Good morning students, welcome back. In this video, we are going to learn about atoms and nucleus, 12th standard physics and NCERT. So first of all, before starting the topic, you should know that this is an important chapter regarding the exam point of view and understanding point of view also. So now just let us start and understand this chapter in the video. Now here what you are going to learn, atomic nucleus. You are going to learn in this chapter Rutherford alpha scattering experiment, distance of closest approach of the nuclear size, impact parameter, compositions of the nucleus, atomic number, atomic mass and atomic mass units, about its details and informations, radius of the nucleus and nucleus density, what is it in it, how it performs, etc. Binding energy per nucleon, means what is energy, what is the reason that atom is a bind with each other with different elements, binding energy curve and its interference, nuclear forces, Meson theory, radioactivity theories, displacement laws, etc. Rutherford experiments, okay, the laws of radioactivity, what is half-life, what is half-period of a nucleus, units of radioactivities, nuclear fission and fission, the most important terms which you are learning from childhood, fission and fusion. I think you have learned in previous classes also. You have somewhat idea. Now here you will learn where it is used, how it is used, what is important of that. Along with that, whole topic on all the chapters, full chapter is dealing with the atom and nucleus. So you have to be that in a smaller size value. First of all, see where it started. It started with the Rutherford experiment. He took just a source, an alpha particle, struck on the golden foil, moving to a fluorescent screen, which can be of different things. Here he has chosen a ZNS screen, so you can see how it is going. So but what happens when it goes with the foil? First, atom can pass through coil. As you can see on the screen, it is how it is moving. It can change the direction, it can reflect back. Again, if it's reflecting back, so there are the various possibility. You can see on the screen how it is going. That is the reason you have the various possibility that the atom is a different structure. So why it is happening? It's simple. The atom structure is such that it has the probability that your alpha beam is changing its direction. It can be a refract, deviate, etc. So graph you can see why it is, how it is done. Now alpha particle is a nucleus of a helium atom carrying a charge of +2 electrons, and the mass is equal to 4 times of hydrogen atom. It travels with the speed nearly of 10⁴ meter per second and highly penetrating. So that you can generally say that it's having a high energy, having a high mass. So what happened? Here Rutherford experiment, and first experiment was Geiger-Müller experiment. So here the sources are different. He took Rn, he took Bi, bismuth and radium. The speed is also a different. He took almost 10⁴ meter per second. He took almost 10⁷ meter per second. Thickness of the gold coil is also different. But what are the observations? Here the first one, the most of the alpha particle passed through a straight line to a gold foil. He concluded that atom is almost having the empty space. Some of the alpha particles scattered. So positively charged and negatively charged effects that. So that is a refraction or a scattering is done because of this, and some are deflected. So there is something inside a nucleus also, because that is because repulsion of the Coulomb force. Scattering is done because of the positive and negative charges difference. Deviation is done or deflection is done because of the Coulomb force. The angle is also important here, that is from where you are striking. The distance of the closest approach of the nucleus size till where the minimum the object or the particle can go to the nucleus, into a nucleus. Suppose this is, as you can see on the screen, the particle is raising in the nucleus, it will reflect back. It cannot go inside. It needs highly amount of energy to go inside. But if it is done, then the other particle is formed. So that your R0 is your distance. When a distance of between the alpha particle and nucleus is equal to the distance of closest approach, the alpha particles comes to the rest. At this point of the distance, the kinetic energy is completely converted into electric potential energy. You can write half mv square is equal to given equation. Impact parameter. So what happens here? See, again, it's scattered or refracted at some point, or it can go straight, but that's not done. So what is that? Theta, or angle formed. Because of that path change, you can see the perpendicular distance of the velocity vector of the alpha particle from the center of the nucleus when it is away from your nucleus is known as impact. You can write b is equal to z e square upon cos theta by 2 by 4 epsilon 0 half mv square. And all other this term has its importance and necessity. The angle is important where it is right. Now, how the compositions of the nucleus is done? You know, proton and neutrons are inside that. Proton is the fundamental particle having its charge and mass. Neutron is neutron but have its mass. Atomic number. So that is the number of the proton on the atom in the atomic number. A sum of the number of the protons and the number of the neutrons in the nucleus is called atomic number. A is equal to Z plus N. So atomic mass unit is 1/12 of the mass of the carbon atom. So that's a reference for any other element for calculation. Now what is the size? The size does not a sharp or well defined boundary. However, the radius of the nucleus can be given as r is equal to r0 a raised to 1 by 3. R0 is 1.2 into 10 raised to 5 meter. That's constant. The radius range is from 1 fm to 10 fm. That is f is equal to Faro. So nuclear volume, you know it's sphere 4 by 3 pi r cube, that's just apply, is directly proportional to the area, and for this the density is also such that you can get by just a simple equation that its nuclear volume is almost 7 into 24 into 10 raised to minus 24. Now what is the discussion about that? Why it is done? Here till now we have read about or known about the size, volume, density. So nuclear density does not depend upon the mass number. Okay, so all the nuclei possesses nearly the same density. The nuclear density extremely large value, such a high density are found in the white dwarf stars. So nuclear density is not uniform throughout the nucleus, that is uneven spread, it gradually moves, you can say that. A nuclear radius of the distance from the center of the nucleus at the density of the nuclear decreases 1/2 of its original. The mass relation or mass energy relation, mass and energy, is equal to mc square. You know this all equation. According to a Newton's second law of motion, you can write F is equal to d dt mv, and m is equal to dv by dt plus v dm by dt. So F is a force which gives a displacement. So energy is increased. So you can write dk is equal to f dx. Okay. Now just after that you have to just make your dk as main subject. So you will write your m dx by dt is equal to dv by v dx by dt. So you can get your dk value. According to the Einstein relation of theory, relativity of mass, that your m is equal to m0 1 upon v square minus c square into half. Now squaring and multiplying this or the term, you can get that your value of m0 square c square, as you can see on the screen. Now just differentiating on these two terms, both the term has the steps you can get the value of dm, make that as second equation. So now you can write from 1 and 2 your dk is equal to dm c square. Okay, now you know that your total kinetic energy is equal to initial to final decay, but decay you have already found, so you can write c square integration of mu 0 to m to dm, so that is m minus m0 c square, or you can write k plus m0 c square. So you consider k as constant, E is equal to mc square, that's, or E is equal to delta mc square. Mass defect, why I said delta mc square? Now see, each of the difference between the rest of the masses of the nucleus and the sum of the masses of the nucleus composing the nucleus is known as mass defect. So you can write the following equation as you can see on the screen for delta m. That is the mass defect of the nuclei is called the packaging fraction, and moreover binding energy is delta mc square. You can say that. So what you can write that your nuclear force are the forces between pp, proton, neutron, proton, neutron, 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 and they can be explained by Meson theory. 3 mesons, pi plus, pi minus, and pi 0. It's 273 heavier than the electrons and 263 times heavier than the protons. Now, moreover, main point of the Meson theory, as we are dealing with the binding energy, that it gives rise to the exchange force between them, and it keep the nuclei in the intact. Second one, it is never permanently over the neutrons and proton, and never permanent on the proton, and keep changing due to exchange of meson. So third, neutron forces arise due to the pi 0. So you will get as emission and absorption theory. Okay, n will give you n plus and pi 0, and n plus pi 0 will give you n. Similarly for proton also, p will give you p plus pi 0, that is emission is occurred. P plus pi 0 will give you p, again absorption occur. Fifth one, neutron and proton forces arises due to the exchange of pi plus and pi minus meson between the nuclei. So you can write n is equal to p plus pi minus, that is emission. N plus pi plus will give you p, that's absorption. P is equal to, or gives you n plus p plus, that is emission of pi plus. P plus pi minus will give you n, that is absorption of pi plus. The time involved in such exchange is so small that 3 mesons particle cannot be detected. Such binding energy of a per nucleon, that's total number of energy of the numbers of the nucleus divided. So you can write as denoted by B is equal to Be upon nucleon per nucleon. Binding energy curve, how it can say, see, consider this here as mass number, Be binding energy in MeV 10⁶, multiply electron volts. So you can see on the screen there are H, H1, H2, H3. The particles are raising H4 as per the nucleon energy. So when it goes on raising and raising, you will see that for the increase in the particles, as the mass number increase, B is also increasing. It will go on increasing, as you can see on the screen. See, just see the points. The points are nothing but the different elements of heavier atomic mass, or you can say a number of atomic numbers are increasing. It will go on increasing from hydrogen, helium, nitrogen, chlorine, argon, copper, iron, and it will go on. And as it goes on, this graph will be seen such that it is continuously increasing with some ratio along with the increase in the energy also. So now see the graph properly, all the points in the graph properly. Okay, it's rising, then it's become stable, almost stable you can say. Means not changing much after a few point. Now see, as you can see the curve drawn. At one point, again it decreases. Why it happens? It is increasing, almost constant for few points. The reason is maximum stability. The objects are maximum stable there. Before that graph is fusion, after that is fission. Okay. Again see the graph. Here, again same thing, you can understand that initially the point showing will give you the fusion reactions. That's why the binding energy is increasing. Okay, as per the A is increasing. That's why you have the H2, H1, H3, He2, He4, Li7, Li6, Be9, Be11 of isotopes, different isotopes of each element. It goes on increasing. Carbon, you have different isotopes. Isotopes means the element having the same atomic number but different atomic mass number. So there are you have to understand and learn. So today I am giving you the simple homework. Find and write the difference between isotopes, isomers and isobars. At least 2 to 3 points for each, along with its examples. Now this will go on, and you have to also understand the meaning of fission and fusion. A simple basic meaning you can understand that fusion. So what is happening there? It's you can say from bigger to smaller. Fusion, bigger to smaller. So big elements are converted into a smaller elements. Fission, from many smaller to bigger. Different elements combine to form a bigger element. This is a basic idea for fission and fusion. Now again we will learn this, but in the detail for the further video. See on the screen, again you will understand that why it is said to be a stable, because that is the maximum reason stability occur. Fusion process is occurring and fission process is occurring. Okay. Now, I want you special features of this is that binding energy per nucleon is very light of the nucleus, such that H2 is very small. Initially there are a rapid rise of the value of binding energy per nucleon. Between the masses of number 4 to 20, the curve shows the cyclic occurrence of the peak, considering to be the your 2He4, 4He6, 8, 6He12, 8He8, O16, 10 and 20 elements, shows that the Be per nucleon is greater than those of the immediate neighbors. Which of this nuclear can be performed by adding the alpha particles to be the preceding nucleus. After A is equal to 20, gradually increase in the Be per nucleon. The maximum value of the 8.8 million volts is reached to A is equal to 56. So that's why the iron is a maximally found in the earth crust. In the earth core, you have the core in the molten form, in the form of lava. So that has the maximum A is equal to 56, where the object is there. So that's why it is the stablest from according to that point of view, and it is the maximum on the this view. Moreover, you should know that binding energy per nuclear of a nucleus having the mass number ranging from 40 to 120 are closest to the maximum value, so that immediately the higher stable and non-radioactive materials are seen. Beyond A120, the value decreases and falls to almost 7.6 MeV for uranium. It is decreasing again, because as the number of the Z and N changes, it depends on that also. The more the proton in the nucleus, the more the energy is lost in binding the energy, or the more the number of the neutron and neutron, it will not affect much. But the more the number of the proton will increase, it will increase the stability factor, but it needs energy to make the object stable. And as it goes on increasing, it becomes a radioactive material. Beyond 128A, the value shows the rapid decrease. This makes the element beyond uranium, trans-uranium elements, quite unstable and radioactive. So that's why we are getting as radioactive. Now moreover, dropping of the curve at mass number indicates that the nucleon are more tightly bound and they are undergoes the fission to becomes the stable. All these features have been seen from the stars to planetary objects also. Stars are showing a fission process. How that we have learned somewhat idea in the previous classes or the previous standards, if you have learned about the universe. Especially it will be a very interesting subject for them, or very interesting topic for them who wants to learn that astrophysics. Astrophysics contain all the study, a deep study of all this thing along with the stars, extraterrestrial objects. So that thing is very important for the chapter point of view. Moreover, the dropping of the curve at the low mass of the number of indicates that the number can undergoes the fusion process to become stable. So in short, the stability of the object, of an element, can be made by itself by a fusion or a fission process. If it's unstable and it wants to stable, it can undergoes a fission and a fission or fusion process. If the energy is more, it will release the energy, and if it's need energy, it will combine with other to make it fission. If it's release the energy, it can be in form of various form. So radioactive materials can have alpha, beta, gamma emission. Even the other elements are also there. If you learn quantum theories, then it will be a very important dealing with this small particles also. For example, a quark also affects in this transitions. Quark, 2 plus or minus 2 by 3 of electrons. Now radioactivity. So what is the radioactivity? Suppose considered plates of positive and negative charge, a lead box having a radioactive source. As you can see on the screen, a radioactive source will transit in such a way that if it contains alpha, it will move to another direction, beta in another direction, gamma in another direction. That is simply because of the charges of the plates in different direction. Alpha is positively charged, will attract to a negative one. Beta, negatively charged, will attract to a positive one. Gamma is neutral, so it will move away straight. Radioactive is a phenomenon of emitting the alpha, beta, gamma radiation spontaneously. Now displacement law says that suppose you have an element ZYA, alpha is related, so alpha is released. So it will give you Z minus 2Y, A minus 4 element. Suppose beta is emitted, then ZYA will be transferred into Z plus 1A, YA. Your A is remaining same, but it is gaining Z plus A. In upper one, it is losing Z because your alpha is 2He4. So 2He4. So that 2 is moving out with that element. So it takes it that 2 element, but beta is electron plus 1, E plus 1 almost. So beta plus 1. So that plus 1 is added. So you will get your Z plus 1 here. But A is remaining same. In a neutron, if it is released, the energy is released. Rutherford and Soddy's laws of radioactivity decay. The disintegration of the radio material is purely random process. It immediately gives out a chance of a disintegration or a decay. First can be told the rate of the decay of completely independent of the physical composition of chemical conditions are material. Okay, now this is directly proportional to its half life. Now you know that. Let's consider that your N is the number of the radioactive atoms present in the element, and then the rate of the decay is minus dN by dt, directly proportional to N. So for removing the proportionality, I am writing minus dN by dt is equal to lambda N, where lambda is the decay constant for disintegration constant for an element. Now rearranging this all term, you will get dN by N is equal to minus alpha dt. Now just taking that term minus dN by dt and integrating that term, you will get your log of N is equal to minus lambda t plus C plus T is a constant. Now at the time T is equal to 0, N0 is the atom, then log of N0 plus 0 plus C will give you log of N minus log of N0 is equal to minus lambda T. So you can just use the log of N upon N0 minus lambda T will, or you can N upon N0 is equal to e raised to minus lambda T. That's your equation. So time of half-life versus atom graph, as you can see on the screen, it's a slope coming down. So that's slope coming down. You can find out your half-life of an object, and 0 by 2 and 0 by 4 and 0 by 8. It will go on decreasing as the time, so it will go on disintegrating its value. Okay, now radioactive disintegration constant lambda. According to the law of radioactivity decay, you can say that your dN by N is equal to minus lambda dt. So first, when dt is 1 second, you can just write dN by dN is equal to minus N or minus lambda. So that can define your relative number of the atoms decaying per second. And hence your N is equal to N0 e raised to minus lambda t. T is equal to 1 upon lambda, then N0 is equal to N E. Or you can just write a simple equation, N by N0 is equal to 1 upon Ne. Okay. Lambda may be defined as reciprocal of the time of N0 falls on to 1 upon E. Now, half-life period. Half-life period is the time required to disintegration of the half of the almost radioactive substance originally present. So you can write N is equal to N0 is equal to half is equal to e raised to minus lambda t. Since e raised to lambda t is equal to 2, so lambda t is equal to log of 2, that is 0.693. So t is equal to 0.693 upon lambda, or you can just rearrange the term lambda is equal to 0.693 upon t. T is the which the material changes from N0 to N. So T is equal to 3.32 log of N0 upon N, and the number of the atoms left behind after the half-life will be equal to N is equal to N0 half or half raised to N. Or you can write this equation in another way, N is equal to N0 half raised to T upon T, small t upon T. Units. Units of radioactivity, Curie, CI, that is activity of the radioactive substance is said to be a 1 Curie if it undergoes 3.7 into 10 to 10 disintegration per second. 1 Curie is equal to 3.7 into 10 to 10 disintegration per second. Rutherford, RD, that is activity of the radioactive substance is to be a Rutherford under it undergoes 10 to 6 disintegration per second. Becquerel, BQ, if it undergoes a 1 disintegration per second. Okay. Now further, these are the other units are also. These are the basic and simple unit which is well known. Now further we have to know something about this, that 1 becquerel is equal to 1 disintegration per second. So 1 Curie is equal to 3.7 into 10 raised to 4 for the Rutherford is equal to 3.7 into 10 raised to 10 becquerel. For nuclear fission, you can say it is defined as the type of the disintegration which heavy nucleus split into a comparable size by releasing the large amount of the energy. For example, you can see on the screen uranium-235 plus striked with the 1 neutron will give you Ba plus Kr plus 3 neutron plus 200 MeV. Okay, now this gives a kind of a chain reaction. Neutron, a thermal neutron is there, uranium is there of 92 and 235, a becquerel and Kr. So you can see on the screen how it starts. One object struck with a bigger object, so it split that object into 3 different element. That 3 will also split other 3 into other 3, and this kind will reaction will go till when it has the energy. So you can say this is the kind of a chain reaction which is giving you a very heavy energy. So here you can see on the screen that n is equal to 1, n is equal to 2 to 9. When just a 1, it is 1. When it is 2, it is 9. When it is 3, then particles become 27. 27. So critical size, the chain of the reaction occurs. The size of fusion of a material must above this called the size of critical size. Critical released neutrons must travel the maximum through a centimeter so that it slow down and causes the further fusion. The size of the material is less than the critical size, then the neutrons are lost. If the size of the equal of critical size, then neutrons produce the equal number of the neutrons lost. If the greater, then vice versa case. Now fusion. Okay, it's a very simple thing that it is defined as the number of the reaction which 2 lighter nuclei merges into a one gives a heavy element. For example, energy source of the sun, proton-proton cycle. HH will give you 1H2 plus electron plus 0.4 MeV. 1H1 plus 1H2 will give you 2H3 plus high amount of energy 5.5 MeV, and it goes on. Energy source of the star, carbon plus hydrogen, nitrogen plus alpha, nitrogen carbon plus electron, carbon plus hydrogen, nitrogen 14 plus alpha, nitrogen 14 plus H, oxygen, nitrogen plus electron. This will go on. So that's a fission process. It will go on and it will give you a new element. Good morning students, welcome back. In this video, we are going to learn about atoms and nucleus, 12th standard physics NCERT. So first of all, before starting the topic, you should know that this is an important chapter regarding the exam point of view and understanding point of view also. So now just let us start